Thank you, Dr. Kemp. As you heard, my name is Clint Stanley, and today I want to introduce to you an example of an orthogonal projection problem in three-dimensional space. It's not quite as bad as it sounds. So first, let's take a look at the problem. We're given that there are 2 points P and Q on the surface of a sphere, which contains the origin, has a radius 2, that's the equation part. And we want to let P1 and Q1 be projection points of P and Q onto the plane y equals 4. And let P2 and Q2 be projection points onto this other plane given by y plus 3z plus 8 equals 0. And our goal is to find the maximum value of 2 times the magnitude of the PQ vector squared minus the magnitude of P1, Q1 vector squared minus the magnitude of P2, Q2 vector squared. Okay? It'll make more sense with a picture. Okay? So again, we're given 2 points anywhere on the surface of this sphere. And what we're considering is the ratio of twice the length of the vector through the sphere versus the ratios of the 2 vectors which are projections onto the 2 target planes. Okay? That's what this says. Yeah. So let's back up and talk about what exactly is orthogonal projection. Okay. Mathematically, if we have a point P in space, and if L is a subspace not containing the point P, then a point P prime in L is said to be the orthogonal projection of P onto L if the vector P prime is perpendicular to L. Okay. Now that that's clear, let's think about it intuitively. Okay? So, if you will, imagine we have a point in space at the end of this laser. And then we have a plane in the space. As long as the angle of our laser is perpendicular to the plane, then the point on the paper is the orthogonal projection. Okay? If the plane's tilted, then we have to adjust the angle of the laser, but not where the point is in space. Okay? I also notice something that will be useful later is that if we shift the plane, then it doesn't do a whole lot to move the projection point. Okay? We'll use something similar later. Okay? All right. So why study projection? Well, oftentimes we want to solve a system of linear equations. Okay? We usually represent this as a matrix. We're looking for the solution X to this system of equations. But in the real world, A is usually overdetermined, which means that it has more equations than unknowns. We have more data points than variables. Okay? And this system usually has no solution unless we have perfect data. Instead, we solve for the best possible solution to the system A x hat equals P, where P is the orthogonal projection of B onto a subspace. Okay? So not the same X, but it's the best possible X. As an example, if we have a point in the plane, a 2-dimensional example, we want to project that point onto a line that forms an angle theta with the axis, then our projection matrix would look like this. Okay? Something to take note of with this projection matrix, and all projection matrices, is that if you look about the main diagonal, okay, then it's symmetric. That leads us to some of the useful properties of projection matrices. If P is a projection matrix, then P equals P squared. That means if we apply the projection matrix to a point that's already in the subspace, we get that same point back. So this is useful. We don't have to worry about applying over and over and over. We get the same answer. It's unaffected. Also, we have the P star there, which means that the matrix is symmetric, and the star takes into account the possibility of having complex numbers as increasing the matrix. So it will be the conjugate adjunct, the conjugate transpose, excuse me. Okay. Also, we have that the inner product of the projected vector with the original vector itself can be given by the magnitude of the projected vector squared, the length of itself squared. Also useful is the eigenvalue can tell us something about the magnitude of this vector. Now, we'd like to simplify the problem that we were given, right? Okay. All right. So since we're using orthogonal projection, the translation of the target planes does not affect the magnitude of the projected vectors. We saw something similar with a point from the laser on a piece of paper. Right? So instead of using the two planes we're given, we'll use the plane y equals 0 and the plane y plus 3z, the square root of 3z equals 0. Okay? Simplifies things a little for us. Also, intuitively, the maximum length of a vector through a sphere, right? If we have points on the sphere, the maximum length of that vector is when the points are on the opposite sides of the sphere. Right? So those are called antipolar points. And that gives us some simplification. It makes the calculation a little easier, which is again more clear with the picture. If we take a cross section of our three-dimensional problem, okay, we have the planes M and N that we just discussed, and we have vector x, the point x on the surface of the sphere. We're taking the orthogonal projections. This is not the xy axis in this picture. They're just some arbitrary axes. And remember that the vector x is on the surface of the sphere with radius 2. Now, using some of our properties that we discussed, we take our original problem and simplify it down. In my opinion, this is the most important slide, but I understand how you feel about it. Okay. What we get down to is that two things. We have a very important projection matrices that we end up with, and we can use the eigenvalue from that projection matrices to maximize this expression. Okay. So first we need to find the projection matrices P and Q. So we find a basis for the plane that we're given the subspace, and that gives rise to the projection matrix. Again, notice that it's symmetric. That's all projection matrices are. Very important property. We find a basis for the other plane, and that leads through some calculations to our other projection matrices. And if you remember, the other piece of that important thing was 2i, so that's a matrices with 2 on the main diagonal. Combining those, we get this matrix. Then we solve the characteristic polynomial for the eigenvalues, and we get 3 eigenvalues since we're in 3 dimensions. We want to maximize the expression we're given in our problem, so we choose the largest eigenvalue. Then we have our original expression, our simplifications, and when we use the largest eigenvalue, that gives us an upper bound on that expression. So it can be no larger than that expression there. Remember something about the vector x. It's from a point on the surface of a sphere with radius 2, so its magnitude is always 2. So that leads us to the maximum value of this expression, which is 25.